Hello, everyone. Thank you so much for joining us today. Our speaker today is Matthew Allen, Professor of Mechanical Engineering at Brigham Young University. Prior to that, Dr. Allen was a Professor of Engineering Physics in Wisconsin-Madison. He received PhD from Georgia Tech and did a postdoc at Sandia National Labs. Dr. Allen has received several awards and honors, including Young Investigator Award from Air Force, Dominici Award from the Society for Experimental Mechanics, and NASA Group Achievement Awards, and several others. He has an extensive contribution in the field of dynamics and vibration, and his recent research focuses on reduced order modeling for structures with energy dissipation and for thin structures with geometric nonlinearity. He has been also the authors of books and book chapters, including the mechanics of jointed structures. Dr. Allen, we are ready to hear your talk.
All right, thank you. Well, thanks everyone for taking some time on a Friday to come learn about dynamics of bolted structures. So we'll dive right in here. The motivation I'm going to use is from the aerospace industry, but there are similar applications in automotive and defense and other areas. But imagine that we're designing a vehicle such as NASA's new SLS rocket. One of the big considerations is the dynamic loads and the stresses that those induce on the structure, and designing the structure to survive all of those loads during flight. And in a vehicle such as this, which actually just the first iteration of it did just fly recently, a couple of years ago, but it tends to be not too hard to come up with a finite element model to predict the loads on any individual piece of the structure. The real challenge is the interface between all of them. So in the development campaign for SLS, there were tests done on pieces of boosters, the core stage, different pieces, such as the Orion crew module and things. And at each level, we could get a reasonable model of the individual pieces, but it's the interfaces and the joints between them that are difficult to model. And why is that? Well, we think of when you have a bolted joint, such as the joints we see on this engine casing here from an F-16 engine, you imagine that everything just is welded together at those interfaces, and so we can model that as a continuum. In reality, though, when you tighten a bolted joint, you get a behavior kind of like this, and this is exaggerated. This is what you'd get if you bolted two rubber erasers together, but the same thing happens with metals, just with smaller displacements. So you get areas of high pressure and areas of low pressure where the slip can easily happen. And so even for low, relatively small vibrations, you can get slip and nonlinearity and energy dissipation. So because of all of this, it's difficult to predict the stiffness of a joint, though there are recent works that suggest it is possible to get pretty close using contact mechanics and simulations like you just saw. But the one thing that no one has succeeded in doing is predicting the damping of a joint. We've had a few studies fairly recently that have come close, but I would argue that predicting the damping of a realistic structure of both the damping due to the joints is something that's still out of reach today. So what do people in industry have to do? They build it, they use past experience to come up with the damping, and then build prototypes and hope that the past experience was correct. Bolted joints are also a huge source of stiffness and damping in a structure. And so stiffness and damping and nonlinearity. And so how do we have to adjust our experimental methods, our modeling to account for that. So we need better ways of modeling joints, and better ways of correlating those models with experiments. And that's what I'm going to talk about today. So here are all the things we're going to hit. We'll talk about simulation methods. Anyway, we'll just dive right into all of that. First of all, before we dive into kind of the engineering scale details, I did want to just point out that joints are influenced by physics at multiple different length scales. For the structural engineer, all we care about is this picture on the left. We know that if we 3D printed our airplane out of all one piece of metal, we'd have very low damping, low energy dissipation. The real structure has higher damping, which is good for survivability, but difficult in terms of prediction and optimization. But that damping comes about due to a variety of effects. I mentioned the contact pressure and stick and slip at the interface, but we can go into even more detail. At the micro scale, the surfaces aren't really flat, so there are asperities. There can even be chemistry and other things that can happen at the interface that influence this. So at some point as engineers, we have to kind of ignore some of the physics and leave that to a test or to other disciplines. And so my talk today focuses kind of on this line and up above, but I did want to point out the richness of the problem. All right, so as we're going through school, you see people doing finite element models, and it's easy to imagine that computers these days are powerful. We can easily just model this, right? Here's a picture of a mesh that you might use to model a bolted joint in detail from one of the references here. And you can model a joint such as this in commercial code such as Abacus, but the computation times are out of reach. There are reduced order models with harmonic balance that have tackled structures such as this with high fidelity, in the matter of like computations that take days or weeks, and unfortunately don't speed up a lot. If you have more processors, you're still stuck with that kind of a computation time. In my group, we've done quasi-static analysis of joints, and that in the order of days, maybe a week. But to simulate a dynamic response, to truly simulate what's going on, is out of reach computationally. And so we need more efficient approaches. So let's go get into some of the physics of a bolted joint. So I mentioned that when we preload a joint, we get areas of high pressure and low pressure. And there have been several studies lately that have explored this to see if you could predict the stiffness of a joint just by knowing the area of the material in contact. So you would solve a nonlinear contact problem such as this, find the area in contact or the area where the pressure is high enough that you consider the surfaces in contact. And these are some pictures from a study we did. It turns out the surface roughness really affects things, and you can see some of that in these pictures using actual topography versus using more simplified or smooth models changes the contact pressure in the area a little. But even considering all of that, our study showed that you could obtain a reasonable prediction of how the natural frequencies change. In this case, we're looking at how the frequencies shift due to preload. So we figure if you can predict that, the change in the natural frequencies as you tighten the bolts, then you have pretty high confidence that you have a predictive and a method that's capturing the physics. So, so this was a few years ago, and we thought this was really promising in terms of being able to predict the stiffness of a joint. And again, it all seems to come down to understanding the contact and understanding the area and the amount of material that's in contact. So that's the linearized stiffness. What about nonlinearity? As you load a joint, the stiffness tends to decrease, and that's because, as we apply a force to the joint, there's an area of low pressure on the outside, as I mentioned. And so it doesn't take very much force before that area starts to slip and the area in contact goes down. And so that causes the stiffness of the joint to go down. And so a typical joint will behave like this. We'll have the linear stiffness. At low levels, it will start to get micro slip where the stiffness drops, usually very imperceptibly. And at some point, you can lose all of the stiffness of the joint. It slips completely. We call that macro slip. And then if you continue to slip, you might even have pinning where the parts would hit the shaft of the bolt or hit something else, and that can introduce even more severe and crazy nonlinearities. We won't get there today. We're just going to focus on this linear to microslip to macroslip behavior. Okay, so that's what happens in terms of the stiffness of a joint. What about energy dissipation? To talk about that, I've put a bolted joint in a 1 degree of freedom system. So we have a mass spring damper type system, well, mass spring system where the bolted joint is the damper. And that way we can talk about damping in terms of damping ratio. Otherwise, we can talk about just the energy dissipated in a joint, but maybe it's a little harder to kind of get a feel for what that means. So I like to think of it in terms of natural frequency and damping ratio. So the natural frequency of a bolted joint behaves just as the stiffness does, as I mentioned a bit ago. And as I mentioned, the stiffness decrease tends to be relatively small, maybe only a few percent in microslip, up to maybe tens or 50% in macroslip. But the damping can actually change by orders of magnitude. So without the bolted joint, we'd expect linear material damping at a very low level. The joint tends to cause damping to increase in a power law fashion. So the log of the damping goes up linearly with the log of the vibration amplitude until you hit macroslip when you can get a big jump in damping and strong nonlinearity. And then beyond macroslip, the joint basically acts like a single Coulomb friction slider whose damping actually goes down as vibration amplitude goes up. So there have been quite a few studies that observe these effects in real structures, and this model with a single bolted joint and a mass spring system can exhibit all of those physics. So that's the kind of the big picture. And again, just kind of to address the naysayers who say, well, my finite element package can do Coulomb friction. Can't I do this? This is a study we did with a cantilever beam with a single bolted joint. You can see the level of resolution that we had to use to capture the stick and slip, microslip to macroslip around the joint. And I mentioned before, even doing quasi-static or a quarter cycle of vibration takes many hours. But I wanted to point this out because that's the 12 hours number is not the whole story. We actually me and some bright students spent 2 years working on the simulations before we actually got physically reasonable results. Why did it take so long? Probably because I'm not very smart, but well, there were some good reasons, hopefully. What we eventually found is in the finite element solver use viscous forces to stabilize the solution as it's iterating on, at each load increment. And those forces can easily become strong and overwhelm the forces that you get due to damping. And so it took a lot of expertise and working on the solver and experimenting with things before we got results that were really believable, and eventually got the results that could match experiments a couple more years later. So I wanted to point that out, but at the end of all of that, you can, in a simulation like this, you can see what happens in the bolted joint. And here you see as we increase the force, or as we kind of move through a quarter cycle of vibration, or you could think of it as increasing the force on the joint, you get the elements slipping on the edge of the contact. So green is slipping and red is stuck, blue is not in contact. And so that's at the interface between this sandwich of two cantilever beams. And as you increase the load more and more, the area of slip increases. And you can use all that information to understand how much energy is dissipated and how much energy would then be lost to damping. Okay, so if once you know all of this, if you can address these solver issues and things, it is possible now to do this kind of a simulation in a matter of hours or days, and to predict the damping that comes from a joint. And we'll hit that again later. All right, so now that we've introduced the physics of a joint, let's talk about simplifications. Most people in industry don't model joints as we've just done because, as you saw, it took a lot of computation just to do one joint, and realistic structures have lots of joints. That's not so practical to do on a rocket or something. So we can use whole joint models to capture kind of the behavior of a joint, capture the physics without having to model everything in detail. So these are all built on the idea of a Jenkins element or a Coulomb friction slider. So imagine we have a spring, we have a normal force applied to a Coulomb friction slider. So this contact has Coulomb friction. And so you know that as we increase the force on the spring, we'll get a linear elastic behavior. And then if we exceed the force, the friction force that's holding the slider in place, then we'll go from being linear elastic to purely plastic, or to being to have pure Coulomb friction sliding. So this has been called a Jenkins element in the literature. And you know, this is the approach that might be used in a finite element model. Every pair of nodes is often treated as a Jenkins element, or you know, a Coulomb friction slider, and the elasticity in the model accounts for the spring. And then you might have, you know, hundreds or thousands of pairs of nodes that are sticking and slipping. So the I1 element is a general purpose model that kind of captures that physics. And the idea is that if we take an arbitrary collection of Coulomb sliders, I1 was able to show that the only thing that matters in the end is the strength of each of those sliders. And as you pull on this distribution of sliders, you can have, you know, at low forces, you might just have one slider slip. At higher forces, more of them will slip. Maybe they all slip. And so you can define a distribution of strength of the sliders, or distribution of normal force times coefficient of friction, that completely governs the behavior. And so I1 was able to do that and show, you know, what behavior is possible with this kind of a model. And so Siegelman came along and came up with a distribution that matched various results in experiments and analytical models, that some of which date back to the 50s. He found that if the strength of the sliders, or the mu n for the sliders, follows an exponential distribution, that will reproduce the power law damping that we see in lots of these tests and experiments. And then he added a Dirac delta term at the end of the distribution to allow it to kind of jump into macro slip at a certain load. So this is Siegelman's 4-parameter I1 model. And it actually captures the exact behavior that I told you about earlier of microslip stiffness transitioning microslip to macroslip, and damping having power law behavior in the microslip regime. And then it turns out in the macroslip regime, it's just a single Jenkins element behavior. So you get a slope of -1 in the damping, log damping versus log amplitude there. So yeah, so that's the 4-parameter I1 element. The mathematical parameters, we usually write the parameters in terms of Fs, Kt, Chi, and beta. We don't need to get into all the details, but there's stiffness, the slip force, the power loss slope, and another parameter. So yeah, and as I said, this captures the behavior that's been observed in a lot of experiments. So it's a powerful model. I wanted to just throw in a comparison to another model that many people are familiar with, just to kind of explain how difficult it is to actually get a model that reproduces all these physics. So another popular model is the Book-Wen model, and it's a hysteretic model as well, and it uses these equations. This is the force in the Book-Wen element, and then Z is a kind of like a slider that's governed by its own differential equation. The Book-Wen model is nice in that it's very easy to integrate. This is much more friendly to computation than the Coulomb slider of the I1 element. And one of my students did a study recently where she compared the I1 behavior to that of a Book-Wen model, and found, though, that with a Book-Wen model, you could only reproduce behavior in a small range. So we could reproduce macro slip for a single value of chi only, not for various values of chi. And you could tune the model to reproduce only that, or you could tune it to kind of capture the macro slip behavior while approximating everything else. But this model was limited, and I bring this up because any model is limited. The I1 element is very nice in its ability to capture this realistic joint behavior. The downside are computational expense. And with any other model, you have the trade-off of fidelity, not having the same fidelity as an I1 model. All right, this is just showing a certain value of chi, a different value of chi, how the model was completely unable to capture the true behavior, the true power law damping versus vibration amplitude behavior there. All right, so can this actually capture the behavior of a real structure? This is a benchmark that Brake and Royce introduced several years ago. So there's 3 bolted joints. It's a lap joint. And we actually modeled it with 5 joints because there's contact at the ends of the beam. Even though they're not bolted, they were pressed in there due to the geometry of the beam. So can we replace that? You can use an I1 model, and we showed in a paper that you could actually replace the joint, each of the joints with an I1 element, and you could use model updating to tune this model to match measurements. All right, but before I explain any of that, I think it's important to cover a couple other concepts. Because imagine what would happen if we did take 5 I1 elements or Book-Wen or any element and put them in this model. What would we have? Well, we have 2 linear beams. We have nonlinear elements. What could we then do? We could do a harmonic balance solution maybe, and try to predict, the frequency responses at different force amplitudes, and we could collect enough of those. We could start to characterize how the behavior changes. But what would we even expect to see in a simulation like that? Because those joints are nonlinear, it's difficult to imagine doing anything but time simulation and looking to see what the behavior is. So what I want to do now is spend a minute talking about the physics that we tend to see when we put joint models in a structure, and relate that back to the modal properties and talk about the advantages and limitations of modal models for this type of thing. Okay, so in this case, for example, the Brake-Royce beam or any structure that has a certain number of joints in it, often we can look at each mode of the structures, first bending, second bending, third bending, something like that. We can take each mode and we can express it as a single degree of freedom mass spring system with an I1 element in parallel with the spring that provides the damping and that provides this behavior that we've talked about. So this idea of taking a nonlinear structure and expressing it as a superposition of weakly nonlinear oscillators is something that's been studied. There's a good paper that explains the theoretical justification in the cases when this can and can't be used, or at least you can explain some of the cases when it definitely can't be used. So this is an approach that can be really helpful. if this approach holds, and I won't go into all the details today, but if this approach holds, then if we take a measurement from a real structure where multiple modes are responding all at once, we can decompose that into the response of each mode. And then we can characterize the natural frequency versus time and damping versus time of each mode. And we can convert that to natural frequency versus amplitude and damping versus amplitude, as you see here. So this is actual data for 3 modes of that Break-Royce speed, showing how the natural frequency does behave just like I told you it would, right? So, hey, I wasn't lying to you. And the damping is increasing. It doesn't look power law here because it's the summation of the linear material damping and the power law. But if you were to subtract off the linear material damping, you would see power law behavior. So yeah, if this modal approach works, then this is a really helpful way to take a complicated structure, complicated vibration responses, and decompose them into modes. So what are the assumptions? You know, this assumes that we have weak nonlinearities. It works best when we have stiffness. The stiffness nonlinearity is weak. So geometrically nonlinear structures such as a clamp-clamp beam will often violate this. We're ignoring any kind of plasticity or nonlinear elastic behavior like you might get with rubbers or something like that. Though, plasticity and joints, I guess, are similar behaviors, so maybe some of that could be allowed. But the biggest thing is that we assume that, the modes are uncoupled. So a force in mode 1 isn't affecting a response in mode 2 and vice versa. The good news is that we can always check that assumption, and I'll say a word about that in a minute. And with joints, one thing that simplifies a lot is that the stiffness effect tends to be small, so it's mostly the damping that we care about. And so we can use an analogy with a linear single degree of freedom system to take measurements and to relate damping, the amplitude of vibration to the damping. And these are some formulas that allow you to do that, either relating the energy dissipated or the vibration to vibration amplitude after one period to the damping ratio. All right, so how does this work on real systems? We'll show you this, I'll show you an example with a 3 degree of freedom system because this is small, it's efficient to simulate, and so we can kind of fully explore the limitations of this assumption. So 3 degree of freedom system with one I1 element is the nonlinearity. That's our truth model. And we'll look at different things. We'll add material damping. And what I'm going to do initially is I'm going to apply a force in the shape of a mode so that we excite the structure in only one mode at a time using an impulse. And then we'll relax that and we'll see what happens as we relax that. So, and then we'll see whether we can represent each mode with a spring mass system with an I1 element to capture the nonlinearity. All right, so if we do that, it works beautifully. So this shows the 3 modes of the system. Now, the big caveat here is we excite it with an impulse in the shape of each mode, or we push this, or you can also think of pushing the structure into the shape of the mode and then letting it go. So this is the best case for minimizing modal coupling. And in this case, the nonlinearity was governed in the physical system was governed by an I1 element. And so the nonlinearity in each mode ends up being really well approximated by an I1 element as well. So here the red is the natural frequency of a modal I1 model, a 1 degree of freedom I1 model. The black dots are the actual measurements, dynamic responses, where you hit this with this impulsive force in the shape of a mode and let it ring down. And the blue is just a simplified equation that reproduces some of the modal I1 models, so don't worry about that one. All right, but what happens in the more realistic case where we hit this on only one of the masses and we excite multiple modes simultaneously? So we did that as well. We'll excite one mass at a time, and we'll assume the modes are uncoupled, use the Hilbert transform to decompose or to figure out the frequency and damping of each mode versus time and express all of that. And here's what you see when that happens. So if we look at mode 2 of the system, we see that no matter where you excite the system, you do see a similar behavior, but you start to see quite a bit of scatter due to the coupling between mode 2 and the other modes. And some actual structures do exhibit coupling like this, where you don't get a single valued function for damping versus amplitude, but you can get scatter due to other modes that are excited simultaneously. The same thing happens for the other modes, though interestingly, for mode 1, it's much less severe until you get to very high vibration amplitudes. So there are different modes that tend to be dominant, and where this is where the modal coupling is less important in some modes where it's more important. And we see that in real structures as well. So anyway, that kind of illustrates what's happening. If we wanted to go into gory detail, what's really happening is, if you imagine we excite the structure at a high amplitude, we excite multiple modes, but then those modes decay with time at different rates. And so if we look at the lowest mode, mode 1, there comes a time where the other modes have essentially vanished and it's dominant. And so we see that the damping initially doesn't follow the backbone curve for the uncoupled mode assumption, but after enough time passes, it does return to that backbone. All right, so hopefully that gives you a flavor of of modal coupling and modal modeling and what it can do and some of the limitations. I wanted to just show a few case studies. We've had success using this type of model on various structures, some of which are getting to be fairly realistic. I'll just show one example. This is 2 catalytic converters. And instead of an engine, so these would be the exhaust on the engine. Instead of having an engine, we just have a steel plate between them. But the joints here are the actual automotive joints with realistic gaskets, realistic bolt torques that GM would use for these parts. And then we test the structure and we measure different modes and we look at their modal behavior. And this is just one sample of the results that we got, but you see we use hitting the structure at various different points on the structure. So each point you hit it at excites a different combination of all the different modes of this assembly. And what we found is, in this case, we got very repeatable results. We got the same behavior no matter where we excited the structure. So the modal model was a hero in this case, worked extremely well to model the behavior, and really simplifies then everything that you do, because you can design a test, you can do your simulations using concepts from linear vibrations. So, so that was a success story. We have other structures where, you could argue there's a little less success. This is one that we have in our lab that's called the S4 beam. It's a beam with 2 bolted joints, one on each end. And when you test this structure, what you see, especially if you're focusing on mode 2, this is the mode that tends to shear the joint and tends to have a lot of nonlinearity. But with this structure, if you excite it at a point that excites both mode 1 and mode 2, then you see this big scatter in the damping and in the stiffness as the nonlinearity is activated. And that scatter is evidence of modal coupling. And so there's opportunity for research here. There isn't an approach right now that can efficiently capture a multimodal multi-mode coupling such as this. The I1 element captures the backbone single mode coupling, but no one has yet invented, as far as I'm aware, a multi-mode I1 model or anything like that that can actually describe this behavior. So there's more work that definitely needs to be done. Even in this case, though, we do find the modal approach to be helpful, because there's usually a minimum value in the damping and a maximum value in the frequency over a set of measurements. And you can assume that that minimum and maximum value is the uncoupled mode case, or that's the case where the contributions from other modes are minimal. And there are some assumptions there, but in many cases, when all the nonlinearities are damping nonlinearities, that works well. And so you can tune a model using that backbone curve and the modal approach, even though mode coupling exists for other scenarios. All right, so I think I've already hit most of these. So the modal model is useful, but we have to be careful because it's only strictly true when one mode is dominant in the response. All right, I'll finish up with one last topic here, and that's quasi-static analysis. So it seems like when we have only one mode responding at a time, it should be possible to speed up our computations, to exploit that, to not have to do these decade-long dynamic simulations for a bolted structure. And it turns out that is possible. So what you can do is, if you imagine this structure bending in mode 2 over many, many vibration cycles, if it's the only mode excited, right, then if the system is hysteretic and a Coulomb slider, then the vibration that happens in one cycle will be the same as the vibration in the next cycle. It's just that that next cycle won't reach as high of amplitude as the first. And so knowing that, we can actually just simulate 1/4 cycle of vibration, just loading of the structure. And from that, we can back out the vibration during all subsequent loading and unloading cycles. So this assumes that the structure obeys something called the Masing hypothesis, which is obeyed by structures that contain only spring slider elements, such as an ion element. But that's basically the idea. So we apply a force that would statically deform the structure into the shape of the mode of interest. We can resolve all the contact to the nonlinearities, and then back out the frequency and damping from that. Now, one thing I want to point out, though, that's the key to this working. This is kind of like a Ritz modeling or a Galerkin modeling, where we say kind of replace the structure with a modal model. Like we could do an eigenvalue problem and replace our full model with a reduced model that contains only this one mode. But there's one very important difference, and that is that we're applying a force, not a displacement, to the structure, and we're allowing the structure to slip at the interface. And so this is not a Galerkin reduction of the beam of the model to one mode. Or a modal reduction. It's a quasi-static approach, and it's important to understand that. But anyway, the idea with this approach is in the modal domain, we apply a force in the shape of the mode, we get the response of that mode. And so in the modal domain, we can look at force versus displacement. We get a loading curve. Masing's rules allow us to construct the hysteresis loop. And then the line connecting the origin to the point of maximal displacement is a secant line that gives a good approximation for the natural frequency of the system. And the area enclosed by the curve gives the energy dissipated, which can be related to the damping ratio. So, hopefully that gives you at least a flavor for how we can use static analysis to predict the dynamic response of structures. We'll show you one little case study where we verified this. Again, we used our model of the Brake-Royce beam. 5 I1 elements was the nonlinearity. And we'd done Hurdy-Craig-Bampton reduction on the 2 beams to make the model faster, easier to simulate, so that we could actually compare true dynamic time response data to this quasi-static analysis. So here are the results. The orange lines are what we would predict using QSMA, quasi-static analysis, so 1/4 cycle of vibration. The blue line is what we get if we actually bend the structure into mode 1, let it go, time integrate until the response rings down, until the vibration dies out, and then use a Hilbert transform to get natural frequency and damping versus amplitude. So the accuracy is really good, but the computation time was amazing. So with this reduced model, it took about 2 hours to generate the blue curves. And as I mentioned earlier, if we'd done that on the full FEM without any Purdy-Craig-Bampton reduction, we'd be talking decades or centuries. How long did quasi-static analysis take? Less than a second. So I like to think of this as a kind of a new framework or an add-on to modal analysis. Basically, linear modal analysis, we solve an eigenvalue problem. We get insight into where the stresses are maximal for each mode. We can think of the response as a superposition of modal responses. And quasi-static analysis augments that by saying after we do linear modal analysis, we do a nonlinear static simulation for each mode. That gives us natural frequency and damping versus amplitude. And so we can still think about a quasi-linear or a modal model and think of the response in those terms. All right, let's see, we're running out of time here, but I guess I've just got a minute. I did want to just highlight a recent study where we tried to use detailed finite element modeling of this S4 beam structure, the structure with just 2 bolts. This is basically where the state of the art is, I think, right now, in my opinion at least. A structure like this with a smallish number of bolts, we can mesh each bolt with enough resolution to predict the stick slip and hence micro slip and damping and natural frequency. So we did this on this structure in the course of a couple days per quasi-static simulation. We could come up with frequency and damping versus vibration amplitude. And we compared that with measurements. So the dots here are measurements from an actual beam. We looked at various models here, different friction coefficients, different ways of approximating the roughness of the surface. And what we found is, it was possible for hopefully realistic friction coefficients, friction coefficients of about 0.2, and with models that captured the actual surface geometry, though with a smooth or simplified representation. Those models did agree with experiments for not just one mode, but multiple modes simultaneously. So, so I believe this is the closest, for sure this is the closest my group's ever come, and I don't know of others who've come really closer in actually predicting the damping and stiffness of a joint from first principles. And now granted, the coefficient of friction that we used is quite a bit different than what people would have thought based on typical values for stainless steel. But if we can believe that mu equals 0.2 is reasonable for microslip friction in a joint, then you could argue that this model is predictive, and we could use it. We used it for other preloads. It worked as well. So there seems to be, no one's really tested the hypothesis yet, but it seems like we're on track to be able to use this type of approach to predict damping in joints. All right, so with that, I'll just close up. I think it's an exciting time to be working on nonlinearity in bolted joints. There are a lot of great techniques that have come together to make these structures, which for many decades have been the bane of the existence of structural dynamicists. We're at the point where we understand them far better than we ever have. We have a variety of methods, and I didn't even hit a lot of methods such as harmonic balance and other methods where we've had good results as well. There's still work to be done in terms of various things. Mode coupling prediction is still in its infancy, but I think there's a lot of exciting things happening. I wanted to just acknowledge many of the students in my research group who contributed to the results that were on these slides. Also wanted to thank Dr. Brake. He provided funding when he was at Sandia that helped me to get started in this area. But more than that, he's led the international community. Well, he and Christoph Schringshackle and Malte Crack have led an international community of researchers that has really advanced this area tremendously over the last 10 years or so. So I wanted to thank him. And with that, also a shout out to my BYU research group, many of which are working on this topic right now. And I'd be happy to take any questions. Thanks for listening.
Okay, thank you so much, Dr. Allen, for a very nice and interesting talk. Let me stop recording here and go back to the participant